Welcome, everyone. How are you enjoying reInvent so far? That's the spirit. So my name is Vlad Vlaschanu. I'm a solutions architect with Amazon Web Services. And with me today, I have Ganesh Subramaniam from Fulfillment by Amazon and Brandon Cuff from Scopely, who will also speak about their experience with AWS. I ask that you hold your questions until the end. We have microphones over there so everybody can hear them. So just by a quick show of hands, how many of you are using serverless architectures or serverless technologies today? OK. So a few of you. That means that at least a couple of you are wondering why we're having a serverless talk in a databases track. In many ways, the answer to that question comes from the tremendous adoption that we've seen with serverless technologies over the last 2 years, and for every imaginable use case. The versatility of these architectures are very compelling, and why would high-performance data be any different? Today, we'll cover a quick overview on serverless architectures and the patterns that we see in high-performance data use cases. And then we'll hear from the folks from Fulfillment by Amazon and Scopely how serverless architectures help them be more agile and optimize their costs. So just starting from the beginning, serverless architectures are here to help you build applications and services. I know that's no surprise to any of you here in the room. But only do that without managing any sort of, or having to manage any sort of infrastructure. No hardware, no virtual machines, or no containers that you have to manage so you can run your services on or your applications. Oops. And you do that by changing what the computational unit of scale is. It's no longer a server hosting a monolithic application or a microservice of some kind. It's the single-purpose function that's the computational unit of scale. Everything else is abstracted from the hardware all the way up to the language runtime. So you can just focus on the code that you have to run. And this has some compelling benefits. For once, there's less development and operational complexity that you have to deal with. And in turn, that increases your agility. And you only execute those functions when they're really needed, which optimizes your own cost because you're actually only paying for the time and a number of invocations for those functions. This is game-changing because functional units and applications fundamentally have vastly different utilization profiles and scaling needs. So naturally, at the center of any serverless architecture is AWS Lambda, the service that allows you to run such functions in the cloud. Only it's the whole ecosystem of services and components that interact with AWS Lambda that actually make that serverless architecture and make it such a compelling proposition. You've got triggers and event sources for functions. You've got streaming data that's being processed by Lambda function. You've got data persistent services, so data can be persisted. Anything that gets processed by those Lambda functions. You've got integration points with other AWS services, with third-party services, integration with your VPC so you can access any sort of resources that are internal to your, affected to your intranet, to your virtual private cloud, or legacy applications. And with all these components of a serverless architecture, data is always the key part of that architecture. Whether that, when you're looking at it, your functions are acting on data. Data is the input, and then your functions are actually processing data. or ETLing that data, or manipulating it in any sort of way to match the business logic. And then, that data then gets persistent somewhere or gets returned back part of your function response. And these create repeatable abstractions that are central to how AWS Lambda interacts with data. You've got Lambda functions that are event handlers. And for these types of functions, the computational purpose of that function is to do something with an incoming event type, and only events matching that specific type. You've got Lambda functions that are acting as serverless backends. And in that case, the abstraction is that API call or the path of that API. And that function is only designed to act on that structure, on that specific RESTful pattern. And then you have Lambda functions in streaming data use cases. Data processing are very strong use cases for Lambda. The abstraction there is a record or a data type. Again, the function will process only data of that type on that specific format. So this not only helps maintainability, but it puts a clear focus on the data that needs to be handled by any given function, process, or flow. It becomes really, really tough in that kind of an environment to build spaghetti code or monolithic applications. And with this in mind, we see two main patterns of adoption for serverless architectures in high-performance data use cases. So one of them is where Lambda is actually playing an active role. This is where Lambda is used part of the workload itself. It's front and center. They're processing your data. Scaling on demand based on how much data is flowing into that system, or it's API driven. Lambda is used to process data, potentially part of an ETL orchestration framework. But in either of those cases, it's front and center there. It's the central part that's driving your business logic. So the advantages in these cases we see around reducing operational complexities. You've got functions that are scaling independently, decoupled of other functions in your application. And you're only paying for that code that's actually running at that point, rather than paying for a host or a service where not necessarily all the code paths might be active at any given point in time. Now, not everyone, of course, can build applications from scratch matching these serverless architectures. And many of us have applications that's been running for several years now. They're not necessarily at the point where they can completely redesign everything. And that's okay. So in those kinds of use cases, we see Lambda working in a support role. So this is where Lambda is used in some form or fashion to optimize a pre-existing workload, a pre-existing application. And there's many really ways you can do that. We've seen use cases where Lambda assists with database utilization. We've seen Lambda use cases where it assists with scaling of a legacy application. We've seen Lambda where it assists with anomaly detection, ensuring that the application works correctly or data access is correct. We've seen Lambda assisting in monitoring and logging solutions. So these are all cases where Lambda is still there, serverless architectures are still there, but they're in a support role, just making sure that the application that you're mainly running is running as effectively as possible. So indirectly, you're still benefiting from cost optimizations, right? You're having a situation where, because your applications runs more effectively, you're saving and optimizing on cost. There's also a couple of other types of advantages in these kinds of use cases. Your applications are more resilient. There's something there watching it 24/7 and ensuring that it's working correctly, and potentially can also actually make it work even at higher performance. And to illustrate the use of Lambda in both these roles, we have Ganesh from Fulfillment by Amazon We'll talk about their serverless architecture for the seller inventory authority platform. And then we'll have Brandon Cuff from Scopely, who will show you how they're using Lambda to detect and track hotkeys in their applications. And with this, I want to invite Ganesh to the stage.
Hello, everyone. My name is Ganesh. I'm a senior engineer at Amazon, working on inventory systems. And I'm here to talk about the inventory data platform that we built with the serverless architecture. With that, I'm sure a lot of you have already done your holiday shopping, or you might have already started your holiday shopping. Show of hands, how many of you have heard the term FBA? Quite a few. Here is an FBA item that is sold on Amazon. And the way to identify an FBA item is, if you look at the seller on record, it has a seller, and next to it, it has fulfilled by Amazon. And FBA items are eligible for free shipping as part of Amazon Prime, free 2-day shipping as part of Amazon Prime. And let's look at how FBA works and what are the inventory challenges in this space. FBA is a service offered by Amazon for sellers to sell their inventory through Amazon by having them send their items into our Amazon warehouses, where we manage the inventory. When the order comes in, we pack and deliver it to the buyer. So seller sends their inventory, we send it to the buyer when the order comes in, and we handle the customer service after the sales has happened. Sellers don't have to worry about managing warehouses or doing the tedious task of fulfilling the item. Buyers get the experience that they always expect from Amazon, fast shipping, great customer service. And Amazon benefits from this by having increased selection, because sellers bring in a lot of items into the marketplace that might not have already been existing. So it's a truly win-win-win situation for the sellers, the buyers, and the Amazon in this platform. So sellers send their inventory to Amazon by indicating how many items they have they're going to send, and we receive it in our warehouses. When we receive it, it goes through multiple stages in the warehouse. We receive it, we might transship it to another warehouse, and then finally it might get stored in some place. During all this process, the inventory level of the seller keeps fluctuating. The inventory gets added into their account when we actually receive it. The inventory will get subtracted when the order is fulfilled, or when we move items from one warehouse to another. The warehouse management systems track these different inventory movements, but they are not responsible for providing an aggregated view of the seller's inventory, and that's where this data platform comes in. We have a number of systems within FBA that use this inventory information, and every system trying to aggregate all of this information would become a very costly exercise. To address this, we built a data platform with the following goals. One, it has to be a single source of truth for sellers' inventory. We wanted to make sure that not every system has to aggregate all the different input, the inventory movements, and trying to aggregate this. Number two, we wanted to have a reconciled view of the inventory. We wanted to explain how the inventory changes from position X to position Y. And lastly, when we are not able to explain it, we want to surface and track those discrepancies. And that's the role of this data platform. So if you look at what are the design requirements for this data platform, it should be able to handle really high volume of input messages. And it should be able to be resilient to handle the hotkey syndrome, which is a very quick burst of events or messages for a single key or a set of keys. One key should not, or transactions for one key should not impact the rest of the processing. It should handle duplicate and out-of-order messages. And we wanted to maintain a complete audit of every single inventory change that happens so that we can go back and explain as to why the inventory position is what it is and make sure that we have complete traceability through the entire pipeline. When we started building this architecture, we wanted to go with a completely managed services because it makes sense to avoid operational pain points that you encounter when you manage your own hardware and hosts and everything. So we chose Lambda as the central component of this architecture. And Kinesis is the stream processing or the stream unit that manages all these events coming into our pipeline. The Kinesis Lambda integration makes it really easy to build these kinds of solutions. So if you look at it, we have warehouse management systems emitting different events into our transaction service. These messages get queued up in the Kinesis streams, and we have Lambda processes that take each event coming in the Kinesis stream and processing it and storing it in our DynamoDB stores. Once it gets into the DynamoDB stores, we have DynamoDB update streams that emit the changes coming from these records or persisted items in the DynamoDB that is further post-processed using additional Lambda functions. And we build an aggregated view of this inventory. Once the aggregated view of inventory is persisted again in DynamoDB, further it gets published into Elasticsearch so that we can easily search across, aggregate it, sort it, and do those kinds of retrieval patterns that DynamoDB is not really good at. And then we use SNS to publish notifications whenever any inventory position changes so that our clients can either get notified when some inventory level changes, or they can come into the system and query from our Elasticsearch store to get the inventory data that they need. Through all of these processes, we have archival front and center. We archive both in S3 as well as in Redshift. S3 is used for typical traditional archiving, and Redshift is used for operational management. If you wanted to go and query what happened to a particular seller's inventory, it's easier to query in a Redshift rather than trying to write an EMR script going against S3. For that, we use Lambda processes that publish the data into Kinesis fire hoses that finally gets into the final end state. So after building this system, if you look back at what the results of this journey was, first, because of the serverless technologies, because of Lambda, Kinesis, DynamoDB, all of them are AWS managed services, we don't really have to spend too much time on operational overhead. We were able to quantify a savings of about 22 dev weeks across this entire platform because we don't have to worry about host monitoring, load balancer monitoring, setting up alarms on hosts, worrying about how to scale for the Q4 holiday peak, and then those kinds of things. These are elastic services that we can scale easily without having to spend a tremendous time and effort in doing this. Again, because of using Lambda, which is single-purpose unit functions, and the built-in integration with the various AWS services, we were able to go from design to launch in less than 4 months, which is a big success for this platform. With this architecture, we were able to improve accuracy of our inventory quantities. And due to that, we were able to save on cost of business operations like seller contacts, which could potentially lead to expensive bin checks where an associate has to go into the warehouse and count every single inventory unit to answer a question coming from a seller. So because of the accuracy in the inventory, improvement in the accuracy of the inventory, we were able to reduce those business operation costs. And our team members loved working on the latest technologies using AWS managed services. So now let me focus a little bit about what were the best practices that we used while we built this platform, and that might be useful for you. So first, we took advantage of Lambda container reuse. Lambda is essentially a stateless execution environment. But there is still an opportunity for us to do costly one-time activities outside the scope of an execution of a Lambda instance. By that, I mean, for example, we use Java and Spring heavily for our event processing. And when you use Spring, you have to build the dependency graph so that the injection happens by the container. And that we were able to accomplish without having to do this for every single invocation of the Lambda instance. And we were able to do it using the container reuse outside the scope of the event handler. This helped improve our performance of our execution units tremendously, which greatly reduced our cost too. Next, everybody is familiar with this. We need to instrument and monitor all our execution environments. With Lambda, it's a little bit more important to do it because unlike traditional computing infrastructure, it's hard to debug and trace in runtime. With Lambda, you don't have access to runtime. So we spent a lot of effort trying to instrument our code, make sure that we have complete visibility during runtime through our own custom metrics and monitors that we have through our code. And we wrote a CloudWatch reporter that essentially takes these custom metrics and publishes into CloudWatch before the execution unit ends in Lambda. So that helped us make sure that we know how our runtime is performing. The other important thing that we spend a lot of time is abstracting the Lambda launch functions from a core entity processing function. And the reason being is that, number one, when we started this journey, Lambda was relatively new, and we were hedging our bets. We wanted to quickly jump into KCL if we have any launch issues with Lambda. That was one motivation. The second motivation is that we wanted to make sure that our Lambda code is heavily unit tested, and by having separation of responsibilities in terms of the Lambda launch functionality from our entity processing makes our code easier to unit test. Towards this, we focused on building our own utilities. One of them is called the Lambda Launch Helper, which is responsible for initializing the dependency graph and making sure that Spring is ready, and then invokes the event handler after deserializing the event that came from Kinesis or DynamoDB stream, and invoking the event handler with the entity so that the entity processor can process that. This also took care of the common error reporting and error handling so that not every processor needs to worry about it, and can also emit these custom metrics, which greatly helps us in our operational aspects. And the last best practice I wanted to share was we used Canary and Canary to help us understand how our system is performing and make sure that our system is meeting our SLA. What I mean by Canary is that we regularly submit synthetic transactions or test transactions into our pipeline so that we can measure when we submitted the transaction and compare it against the end state and make sure that the transaction went through the pipeline, as well as whether it met the SLA. So every few seconds, we submit these transactions, and it helps us monitor whether there's a backlog somewhere because our test failed, or whether it meets the SLA. And this is a critical tool in our pipeline to make sure our health of the system is really good. We use Kinesis shard level metrics to know when a backlog is building and make sure that we have adequate monitors around it. Here's a sample dashboard that we use, some of the metrics that we use. Average transaction processing time for the end-to-end system. How many transactions, how old are the transactions in our backlog, as well as what is the Canary processing time. And if any of these fails, we can be alerted so that we can go and investigate into this. With this, I will call Brandon, who's going to talk about the serverless architecture that they built.
Hi, everyone. My name is Brandon. I'm a senior engineer from Scopely. So Scopely is a mobile game company. We have several games, but the ones I'm going to talk to you today about are Yahtzee with Buddies, Dice with Buddies, and Wheel of Fortune Free Play. So Yahtzee and Dice are pretty simple games. They're player versus player turn-based games. So one guy takes his mobile client, he rolls some dice, he makes a choice, submits it to the server. Server sends a push notification to the other guy plays his turn, and then they go back and forth until the game's over. And then maybe they win some achievements or a tournament or a prize or some currency. Wheel of Fortune has a similar game mode, but there's a longer duration between server trips because you're spinning wheels and guessing letters and things, which takes a little longer. So we're not Netflix, but we do have some pretty decent traffic. We have over 6 million daily active users, 1 million requests per minute, and 100 plus API servers. So here's a basic layout of our architecture. Like Vlad said earlier, we're not using Lambda in our primary role. It's playing more of a supporting role, but I'll get to that later. So right now we're running EC2 instances behind an ELB. The mobile clients will make HTTP requests to the ELB. And then the instances will talk to Memcached, Elasticache, MySQL, and DynamoDB to serve the request. So in order to serve a request, the application needs access to a couple different types of data. Some of it is just meta information. So this is stuff that's shared between all users. It's like what tournaments are currently running, when they start, when they end, what achievements are configured, that sort of thing. So this kind of stuff, it's really small. The PMs configure it in a website. So our application servers just pull it out of MySQL every minute and then keep it in local memory. So this use case is really trivial and easy to scale. Well, there's not really any scaling. Our second type of data is more interesting. It's our user-specific data. These are things like the actual game documents that the user are playing on, the achievements that they've completed, like what they scored in a tournament, that sort of thing. So anything that has to do, that goes with the user, we typically put in DynamoDB because we have a lot of user data. And we don't really want to worry about getting up in the middle of the night and having to shut down our RDS instance and upgrading it and that sort of thing. We'd rather just go to DynamoDB or use a tool that automatically scales up DynamoDB on demand. Cool. So about DynamoDB, so theoretically, you can scale up as much as you want within a region. And this is possible because under the hood, DynamoDB will break up your data into partitions so that multiple servers can actually work on that data. And then each record that you have in DynamoDB has what's called a hash key. I think they might call it a partition key now. But that key tells, DynamoDB uses that key to map a particular record into a partition. So when you provision a table in DynamoDB, these partitions are transparent to you. You just say, hey, DynamoDB, I'd like to be able to read 4,000 records per second. And DynamoDB under the hood allocates enough partitions to handle 4,000 requests per second. But each partition has its own upper limit on how much throughput it can actually handle. So when you exceed the throughput of a particular partition, you'll get a throttling error. And then typically clients will do an exponential back off or something so that to slow down. But usually we like to avoid the throttling errors to begin with. So in this situation, I have a table that has 4,000 reads per second. So if my client tries to get the record for user 123, 2,000 times per second, even though the table capacity is 4,000 times per second, it's still going to get throttling errors because it's exceeding the limit of its partition, and that record only lives on one partition. So when this happens, we call it a hotkey. So a hotkey is like one key that's accessed more frequently than the other keys. And in order for DynamoDB to work really well, you have to sort of distribute your load across the keys evenly so that one partition doesn't get overwhelmed while the other ones are just sitting idle. And in this, we have a couple of CloudWatch graphs on the slide. The top one is showing that we're currently experiencing throttling errors on our gets. And the bottom one is showing, see the red line is our provision capacity for a Dynamo table, and the blue line is our actual consumed capacity. So this is sort of the classic symptoms of a hotkey. We're under-provisioned, but we're still seeing throttling. So I don't know, how many of you guys have seen this sort of situation before? Cool. Yeah. So this happens a lot. So let's see. So at Scopely, since this happens all the time, we try to come up with better ways of attacking this problem. So one way you can attack the problem is to just put some cache nodes in front of it, and that sort of works for a while, but generally when we run like memcached, we run it in a cluster, and you have, each key is going to sit in a particular node in the cluster, and you're going to eventually overwhelm a particular cache node as well. So that doesn't really get you all the way there, but it might work for a little while. Another thing that you can do is, the best thing to do is really to solve the underlying problem. And that can be sort of a whole bunch of different things. It's usually a bug of some kind or just an oversight. But detecting it is usually the hard thing, because you have to, I don't know about you guys, but in our code, we have like, millions of lines of code, and sifting through it and finding like where this hotkey might be is kind of difficult. So it's really nice to know what the key is. That really helps find the problem, but the CloudWatch metrics don't tell you, so that's unfortunate. So to find the key, we could do a couple of things. I mean, we could pop up Wireshark and try to sniff traffic and look for the key, and that doesn't really work over SSL, so it doesn't work for Dynamo. It does kind of work for memcache, but it's not very convenient. Another thing is you can put some code in your application to just log a key every time you request something, but that adds a ton of overhead, and it takes up a lot of space in your logging cluster. So what we really want is a solution that we can turn on all the time, has minimal performance overhead, and doesn't cost a lot of money in storage. So we came up with this solution. So what we do is we have our application servers have a bit of tracking code in it, and it keeps track of the top 10 most frequently seen keys in our memcache client and in our DynamoDB wrapper client. So like the straightforward way of tracking the keys is maybe just to have like a hash map where you have the key is the key and the value is a count. But if you're running through like 100,000 requests per minute on a particular application server, you have to use a lot of memory to do that for every period. So we cheat a little bit. We use a probabilistic algorithm, which called count-min sketch. But this allows us to sort of sacrifice a bit of accuracy in our counts. And the trade-off is that we can use a fixed size of memory to track an unlimited number of keys. And that works pretty well for us because all we really need to know is the relative difference between like how hot one key is compared to the average. So here's a quick overview of our, so like once we get those top 10 keys in our logs, it gets pushed into our logging stack. And this is what that looks like. So this is sort of Lambda in the supporting role. We have our application, and we have a little sidecar process that runs on our application that aggregates our logs. And it shoves that into Kinesis. Then we have a Lambda that reads from this kinesis and pulls out interesting information from the logs. So all the typical things like the timestamp, what host it came from, what game it came from, and other use case specific information like our hotkey information. So once it pulls out and parses all those logs, it shoves the Elasticsearch, or shoves the documents into Elasticsearch service, and then we can use Kibana to build dashboards and have nice, pretty graphs and that sort of thing that give us some quick insight into what's going on. And Lambda works really well for this scenario because there have been several times where our application has some log information, but it's not indexed yet. And it's really nice to be able to say, oh, hey, I'd like to really index that information and then make a graph out of it without having to wait for the next sort of deployment cycle of our application. So Lambda makes it really easy because I can just, add a regular expression to that code that pulls in the values into the document and then just hit deploy. And within minutes, I'm getting my new indexing information. It also makes subscribing to Kinesis really trivial because you add shards to Kinesis and you don't have to think about adding more subscribers and that sort of thing. So that's really convenient. But back to the hotkey detection. So once we get our hotkey events into Elasticsearch, this is sort of what they look like. I mean, on the top, you'll see the log line. So that's what the application servers actually log when they log the top 10 keys. And then this is the Elasticsearch document that gets produced once the Lambda is finished with it. So in there we have like a category of what the hotkey thing is that we're tracking. In this case, it's gets on memcached. And then we have the key. We have the estimate of how many times that key was encountered. And then the total count is the total count for the category for all keys. And then the frequency is the ratio of those two numbers. So once we have all this stuff in Elasticsearch, we can build a dashboard that looks sort of like this. And I'm going to show you how to build it real quick. Okay, so here I have a basic dashboard already built out. I do have that. Okay, let's get rid of that. We have a couple of things in here already. So we have like a date histogram of the log messages, which games the log messages came from, and the top hosts. But we don't have our hotkey information yet. And also you'll notice that it looks there's like an odd traffic pattern to the logs. And that's because for this demo, I just wrote a Lambda that gets invoked once a minute. And it shoves a bunch of fake hotkey documents into Elasticsearch. But so this isn't our actual production dashboard. But so to make the hotkey thing, we'll go to visualize, and I'm going to use a data table since it's a little bit easier to see than the bar charts. And what we want to do is we want to add up the counts, and then we want to break it down using a terms aggregation on the keys. So I'll do top 10, and then I'll hit that green button. And then right away we can see we have a couple of hotkeys in there. So user.0 and user.-1 are getting a lot more hits than the rest of the users. So I'll hit save on this guy. And then I can just add it on my dashboard. Like so. So it's pretty easy to build one of these things. And how do I go back? Okay. Cool. So results and lessons learned. So one thing is once we deployed this thing, we found so many bugs, way more than we thought we did. Most of them were in Memcache because Memcache has a much higher throughput ceiling on the nodes. So when we had a hotkey in Memcache, it went unnoticed for a long time. But when we started playing with this dashboard, we fixed like 5 things right away. We had like special case user IDs, like the one that I showed you in the demo. So we had some requests that would, when you weren't playing against an actual person, it would send you down a user with an ID of -1, and we started requesting -1 in our database and stuff. And then you'll see that we also had things like configuration objects that were, instead of being cached locally in memory like they should have been, they were cached in Memcache, and they were all on the same node. And you can see, like, we took a look at our CloudWatch metrics after we found this, and then we noticed that, hey, look, one of our nodes is sending a lot more bytes out of it than the rest of the nodes. So we also discovered that large keys could be detected this way. So we had intermittent timeouts on Memcached, and we kind of had a suspicion that it was for very large objects that we stuck in there. And so we used sort of the same hotkey detection technique, and instead of, we just made a slight tweak to it. So instead of incrementing by 1 every time we saw a key, we incremented by the size every time we pulled something out of Memcached. And then that gave us a view into what the biggest objects were in our Memcached system relative to the whole. And we found some interesting things, like we had some users with a meta information document for that user that had like a little embedded list in it of recent users that you played with, and that just kind of grew to infinity for some users. So we just ended up fixing that by trimming the list or moving it to a different storage system. But yeah, the large key detection was really useful for finding those sorts of problems. We also caught a bot, and that was fun. So like one day after we had already built this thing, our average response time went up like crazy, but our median response time was okay. So it was just a slice of traffic was having really poor performance. And we noticed a bunch of throttling in DynamoDB. But yet we were still under provisioned. And we took a look at our dashboard and we noticed, hey, this guy's user ID is showing up all over the place. We looked up his account and deleted it, and kind of solved the problem right away. And then we were able to we just played whack-a-mole with this guy for a while until the next release, when we implemented some rate limiting, per user request rate limiting, that sort of took care of the problem for good. We also caught some bad client behavior. So our iOS client sort of did the right thing. And when you have a game list, so the iOS client would pull the game list, and then when you actually wanted to play the game, it would load some extra game details that you needed to play the game. So our Android client would pull the game list. Then in the background, it would make a request for every single game you had in your game list. And some users had thousands of active games running. So every time they would refresh their game list, they would, it would hang forever. And the server would also return a bunch of errors, and they would get a bunch of nasty dialogues and that sort of thing. And this went unnoticed for a long time because there aren't very many users that had that big of a game list to cause problems. But after we got rid of all these hotkeys, we noticed that some users were still showing up in it. And then we filtered it down by the client platform, and we noticed they were all happening on Android. So we kind of took a wild guess and thought maybe it was poor client behavior, and looked into it, and then talked to the client guys to fix the problem. Anyways, thanks for listening. There's my email address if you have any questions.
All right, thank you all for attending. I was really happy that you chose to spend the time with us. Before you go and we open up the floor for questions, I wanted to remind you to kind of fill out your evaluations. Your feedback is invaluable for us and helps make re:Invent better. And there's a couple of related sessions that might be interesting if you want to look more into serverless architectures, patterns, and best practices, or dive deeper into services such as DynamoDB and Elasticache. And we're all both Brandon, Ganesh, and I will be here available for questions if anybody that is interested in finding out more. And thank you so much.